All right, we are continuing with kinematics values, picking up from displacement and distance. We had left off with two values, one a vector, one a scalar. So displacement is our vector value describing how far something or someone goes. Distance is a scalar that answers the same question. We're going to keep going through that list of questions we came up with. How far does something go? How fast is it going? Speeding up, slowing down, and how long it takes to move. Now, a lot of these, especially just looking at the words velocity and speed, you've seen them before. It's not that you didn't know velocity was referring to how fast something was going, but of course, we're going to come up with specific definitions. We're going to talk about vectors versus scalars. We're going to describe units, variables, and we're going to talk a little bit about some things like average velocity versus instantaneous. We'll talk about how acceleration shows up and works in our problems, because these are all going to be some important context and foundation for solving kinematics problems, knowing not only just what velocity is at a basic level, but how do we use it, what do the different variables mean, and what are some equations that we can use with this. All right, velocity and speed. These both answer the question of how fast something is going. Move this. All right. So in motion, when an object moves, how fast that object moves is velocity or speed. All right, so we'll take velocity first. There's probably the most to say about that one. And velocity is a vector value describing, well, exactly what we said above, how fast an object moves. Okay. Um, yeah, let's get right into. There's not much more to say. With displacement and distance, we clarified some things like displacement is from initial position to final position, regardless of the path taken in between. Velocity, there's not much to say other than it's a vector, so it has direction. So something like 5 miles per hour north is a velocity, but you do need to have that direction on there. Okay, let's look at units and variables. So our base units, again, this just means, like we talked about in the last video, base units simply means we want every value of velocity to be in these base units before we start plugging it into equations and working with it, because there's lots of different units you could use, miles per hour, meters per second, feet per second, just to name a few. But we're going to be sticking with meters per second, abbreviated M over S. So meters per second is the default we're going to be using. And if you, for any reason, you really shouldn't, I don't think AP will give you any, but if for any reason you have units that are not meters per second, you'll need to convert them into meters per second. All right. Variable. And I'm going to say variables because, well, there's really one variable, but I guess I should say variable. Oops. Where am I going? There we go. Nope. There we go. All right. I don't know what that was. Control V. There we go. Oops. Forgot. There we go. We've done it. The variable for velocity is V, unsurprisingly. But we have a lot of subscripts. It is a vector, so we make sure the vector sign goes above it. We're going to have lots of different types of velocities popping up. So indicating final, initial velocity, average velocity, x velocity, y velocity. So let's put in parentheses. Well, let's just do this. V is the variable. We may see things like V final, this would be final velocity. V initial. Now, we talked about this a little bit. Um, there's alternate ways to write these. I'm going to do those in a different color down below. Well, I'll just do like a little arrow. V final could also be written as just V. You'll see that sometimes. V initial, sometimes written as VI instead of V0. There's a number of options for this. Um, both VF and V would indicate final. Both V0 and VI would indicate initial. So there's some options there. And AP is fairly consistent with they like to use just V for final and V0 for V initial. I am pretty used at this point. I'm pretty used to using V0 for V initial, but you'll see me if I'm doing a problem or notes on the board or something. If I'm writing something out, I'll probably do V final a good amount of the time because I do like it. I think the F is pretty clear as to final velocity, but just be comfortable with as much as possible. Try to be comfortable with recognizing you could do VF or V. Those both mean final. V0 and VI for initial. All right. Other options that we'll see, V average, we'll talk about that one in a second. Average velocity, so subscript AVG. Vx and Vy, because we will be talking about horizontal and vertical velocities and using them in equations because when we talked about math with vectors, if we take a velocity, which is a vector, and we want to put it in an equation where vectors are being added or subtracted, which the vast majority of our equations will have some sort of addition or subtraction in them involving vectors. When we did that back in the vectors introduction, we made sure they were in component form because the components, like the I hats and j hats, when we used those for x and y, we had to add up all the I hats to get the x direction result, add up all the j hats when we're adding vectors to get the y direction vertical result. And for that reason, we are very often going to look for or find or use the x and y velocities. So you'll see those a lot. You can actually also start combining these. So if you want to know what was the horizontal velocity, how fast was this object moving horizontally at the beginning of whatever time period we're like looking at, you can combine them for like V subscript X subscript 0. And we'll start doing that in some of our problems. You'll see that. But you could do like VY final or VX initial or something like that. So you'll see them, those subscripts can get combined, but we don't stack up more than two subscripts usually. All right. So those are the variables. All right, and this leads us to a spot where that middle one, V average, is significantly different than the others to the degree that we want to talk about it. So when we talk about equations, especially for finding velocity, there's a very important difference between average and instantaneous velocity. So we're gonna distinguish between average and instantaneous velocity. Instantaneous velocities would be all the other ones besides average. So final and initial velocity are the most obvious with this because if you're looking for final velocity, let's say, excuse me, let's say the problem that we are solving has a 5-second time interval. We're looking at what happened in those 5 seconds. At the beginning of those 5 seconds, we have an initial velocity. How fast was the object moving right at the beginning of that 5 seconds we're looking at? At the end of that time, it has a final velocity. Those are instantaneous velocities. At that split second in time, right when we started looking at what's happening with this object, how fast was it going at that split second? And final, same thing. Right at the very end, at that exact moment, how fast was it going? Same thing with Vx and Vy. When we talk about Vx and Vy, I guess those ones you could put them together with average. So I guess I should say VF and V0 are instantaneous. V average is not, it's average. And Vx, Vy could sort of go into either because you could find an instantaneous X or Y velocity right at the beginning or end of a time period, or you could find an average x or y velocity. On average, how fast was it going horizontally or vertically? So instantaneous, I guess we can do a different color. We'll do some crossover. I didn't order these in the best way, but there's your average velocity, and then these would be your. I'm gonna wind this arrow around here, and these would be your instantaneous. Go above. All right. So instantaneous velocities versus average. All right. Cool. Let's define those a little bit, talk about them, and look at some equations. So average velocity. It's kind of in the name, I suppose, but it is simply the average of how fast an object traveled during a time period. Average of how fast. And keep in mind, because it's velocity, it's still a vector. We'll talk about speed, and you could have an average speed, but this is velocity. There needs to be a direction on it. How fast an object traveled during a given time period. Now, when it comes to equations for this and how to calculate it, I guess another thing we should add is it's this average. And the key to average velocity is even though that velocity that our object is experiencing or is moving with, I guess, experiencing is more like acceleration because that indicates some outside force acting on it, which we'll get into later. But even though that velocity that the object moves with or has, that velocity may change during the time period. Okay. So right, a great example of this is you're just driving from Crozet to Charlottesville, and there is a direction. So from Crozet to Charlottesville, I don't know exactly. I mean, I would generally say east, but it's probably not due east. If you drove from Crozet to Charlottesville, we could say east is the direction, but as you take your trip in your car, you're not going the same velocity the whole time. You're not even going the same direction the whole time. You got to turn on some streets, and generally you're going east. And while you're on like 64 or 250, you're probably going east most of the time. But so let's say you go south for a little while to get on the highway, and you're only going 25 miles an hour, and then you hop on and you speed up, and you get up to 70 or 75, and you maintain that roughly. You pass somebody or you slow down or whatever. Then you get off your exit, and now you're slowing down a bunch more, and until you get to your destination, you might be going 35, 25 miles an hour to get to wherever you're going in the city. So all those changes in velocity, both the magnitude, how fast you're just going as a number, and the direction as you're turning different ways, your average velocity would simply be on average, like how fast did you go? And it might end up being 60 miles an hour or 50 some miles an hour, depending how long you've spent on the freeway or how long you spent on smaller or slower roads. So that's that average, right? Even though you drove at different velocities throughout that time, if you just gave one number and said like, well, and we're about to get into the way that you would find that average velocity. Turns out there's an exact way you could calculate it. So let's talk about an equation. So the equations to calculate it, one is displacement over time. Now we're sort of giving away the time variable, but that's fine. Time isn't super complicated. So change in velocity over change in time. So the time period is just how long it takes you, maybe 20 minutes to drive to Charlottesville. And the displacement is, remember, that's final and initial position, the difference between them. So if you did that calculation, you took point A and point B, you found the straight line vector displacement between them, and it's not only horizontal. I guess, well, there's some hills in there. But yeah, let's say it was, I don't even know the exact number, maybe 15 to 20 miles, 15 miles in 20 minutes. So you would take, if you were looking for miles per hour, you would take your displacement, 15 miles, or whatever it ends up being exactly, divided by the time. 20 minutes is a third of an hour, so 0.33 hours. Um, and that would give you your average velocity, right? You would just take the total displacement you traveled in that time divided by the total amount of time that it took you. That will give you your average. Okay. And again, if we did that calculation, see, divided by 0.33, if it was 15 miles, I think the 15 divided by 0.33, you drove 15 miles in 20 minutes, it would come out to about 45 miles an hour, which is significantly less than your freeway speed because maybe you ran into traffic or you slowed down or whatever. You just drove slower on the side roads or as you were getting in and out of the cities. So, yeah, that's one way that you can calculate average velocity. Take the total displacement during whatever time interval you're looking at, divide it by that time, and there you have it. Now, there is another way to do this, and that is actually dependent on your starting and ending velocities. This wouldn't work for your trip to Charlottesville, but it will work for the kind of problems we're going to encounter where when we get to acceleration, we'll talk about acceleration being constant. Your acceleration would not be constant as you hit the gas or brakes. You're going to have more or less amounts of speeding up and slowing down as you go. But in our problems, we're going to assume constant accelerations. So average velocity can also be found with your starting velocity plus your ending velocity, v initial plus v final divided by 2. And that is a more basic way to take an average, add all the things up, divide by how many things there are. That's your basic mathematical average equation, right? Is add everything up, divide by how many there are, and then you'll find the average. Right? It's like if you have back to elementary school or whatever, you've got all the kids with their apples or oranges or whatever it is they've got, and say, okay, this person has 6, and this person has 12, and this person has 17, and you divide by how many people there are, you found the average amount that people have. Okay, now that again only works when the acceleration is constant, but that's going to be the case for all AP problems. They don't go into situations where the acceleration starts changing all over the place, even though in real life that happens. Okay, so that's average velocity. We don't use it a ton, but you want to keep your eyes out for it because if it shows up in a problem and it says average velocity, that is different from instantaneous velocity. So we'll write a quick description of instantaneous here. So that instantaneous velocity that is just how fast an object is moving at one exact moment in time. At one exact moment in time. All right. Oops. Putting my words in the wrong order. One exact moment in time. All right. Also to note about velocity, if you were to read your speedometer, but add a direction, that would give you your instantaneous velocity. So where you drove to Charlottesville with average velocity, you said, all right, I went 15 miles. It took me 1/3 of an hour. So I'll divide 15 by 1/3 and get my miles per hour average velocity, which in that case would be 45. Instantaneous, okay, maybe you're on the ramp getting onto the freeway and you're speeding up and you glance down at your speedometer and it says you're going 60 miles an hour. Well, at that exact moment in time, you're probably going to speed up a little bit more because the speed limit is 70 on 64. But if you're going 60 miles an hour, that's your instantaneous velocity at that exact moment in time. And then you keep speeding up, and a little bit later, it's 62 and 68 and so on and so forth. Okay. Now you would have to add a direction to that because your speedometer gives you speed. It doesn't include a direction. I'm sure some newer fancy cars could tell you exactly what direction you're headed, but uh, you know, if you're going generally east, you could put two and two together and say my velocity as I'm getting on the freeway is 60 miles per hour to the east at this exact moment in time when my speedometer says 60. All right, equations for finding this. We're looking at specifically v initial, v final. Those are those instantaneous velocities right at the beginning or end of whatever time period we're looking at. We can find those. There are equations for them, but those are going to be part of our big five kinematics equations, which will get introduced soon enough. Okay, solid. That's pretty much it for velocity. We've got units, we've got some equations already when it comes to average, and for calculating or finding instantaneous velocities, we'll get to that with our big five kinematics equations. Okay, let's look at acceleration. So, acceleration. Oh, wait, oops, I'm skipping ahead. I am very much skipping ahead. Let's do speed. Let's do speed. All right. Speed is a scalar value describing how fast an object moves. And this is going to be really short and sweet because speed, unlike distance, where we had to mess around a little bit with, okay, distance could be the total ground covered, the like longer path that you took from point A to point B, and that total, like if you were on a run, you'd want to know how many miles as you wound around and went hither and thither. How many miles did I go total, not just from point A to point B in a straight line. So there was some important distinguishing between displacement and distance, the vector and the scalar, for describing how far something goes. Speed, not so much. I mean, there's a distinguish between them. Speed doesn't have a direction, but when it comes to speed, this is really just the magnitude of velocity. Meaning you don't have to do any extra work to go from velocity to speed. In fact, you would just take something off of it. So if you looked down at your speedometer and said, it said 60 miles an hour, that is your speed without direction. If you did a calculation for velocity and found, oh, my velocity is 6 meters per second to the right, you don't need to do anything additional to find speed. Just leave off the direction to the right, and that 6 meters per second would be your speed. So speed, we don't even bother with equations for it really, because if you need speed, if you need to find it, just use an equation for velocity, and once you find that velocity, just don't bother with the direction. Don't worry about it. Leave off the direction. The same thing with average. So you could have average speed, but that's just the magnitude of, right, the number and unit for average velocity. If your average velocity is 12.6 meters per second north, then your average speed would be 12.6 meters per second. So it is just as simple as finding the velocity and then taking the magnitude of that, but we'll throw it in there. Okay, now we can do acceleration. We don't even have variables. Like we use speed so infrequently that sometimes they'll do velocity v with absolute value signs to indicate we don't care about direction, positive or negative, or velocity, anything like that. It's just the absolute value or number of how fast you're going. You could use S for speed if you really wanted, but S for speed as a variable doesn't really show up. And the units are, of course, the same, just meters per second, same as velocity. So, all right. Let's look at acceleration. Acceleration answers the question um, of how much an object either speeds up or slows down or changes direction. And there's no pair of values. It's not like displacement and distance, velocity and speed. Acceleration just is a vector. There's no scalar equivalent here. I mean, you could still give the magnitude of direction, or sorry, the magnitude of acceleration without a direction, but acceleration itself is just a vector value that has direction with it, and unless a problem specifically asks for the magnitude of acceleration, you'll always include that direction on there. All right. Cool. So that is acceleration. Um, yeah, let's do the units. So our base units for acceleration are meters per second squared. We're going to talk about this a little bit because these are challenging for people. If you want to abbreviate, meters over seconds squared. Now, this is the place where people get confused the most between acceleration and velocity. People will flip these units in and out. You really don't want to do that, right? Speed or velocity is meters per second. It's how far do you go in what amount of time, right? Meters over seconds. Think of the equation right up here, displacement over time, right? Meters, displacement, time is seconds. So meters per second is velocity or speed. Acceleration, I'm not going to get into calculus stuff too much, but acceleration is the rate of change of velocity, meaning your velocity is just how fast you're going. When you accelerate, that velocity changes. And at what rate it is changing gives you acceleration. So a way that I like to think about the units of acceleration, you don't have to write this, but I'll write it just for briefly here as an example, is you could do meters per second per second. That at least helps me visualize, hey, acceleration is a change in velocity. In the numerator here, I've got meters per second, my velocity, it's changing. Could be increasing, could be decreasing, could just be changing direction as well. So speeding up, slowing down, or changing direction. And then as that velocity changes in some amount of time, a really big acceleration is if you go from 0 to 60, which is a pretty big change in velocity for miles per hour or meters per second. So you go from 0 to 60 in 0.5 seconds. That's crazy, right? That's a huge acceleration. No vehicle or car that we have would go from 0 to 60 in 0.5 seconds. That'd be insane, and the human body would not appreciate that large amount of acceleration. So if your change in velocity is really large and your time ends up being really small, you get a huge acceleration. We'll see that more when we look at the equation in just a second with the variable. But that sometimes helps me to just say, hey, we could also write this as meters per second over seconds. Change in velocity in some amount of time. All right. But that's sort of leading into our next couple bits, which is variable first. It's just A for acceleration, and we will see, actually, I guess the only ones that we'll see is like AX and AY. I was going to start talking about all the stuff like we had with velocity, but of course, acceleration, we're not going to have acceleration that changes throughout a time period. So we don't really have to worry about initial and final. If you're looking at a 12-second time interval for a problem, your acceleration, even though you might get one number for acceleration for the first 5 seconds, and then one different number for acceleration for the last 7 seconds, over that 12-second time interval, your acceleration isn't increasing or decreasing as time goes along. So you don't really have to worry about what acceleration do we start at, what acceleration do we end at as it changes in between. We're not going to have that. Even though the real world that happens, it just makes things more complicated, and we're taking things a little more simple here. So don't worry about initial and final acceleration. But we will see horizontal versus vertical. Like how much is something speeding up horizontally to affect the x direction motion? What acceleration is there vertically? Like gravity is a big one we'll look at, of course. Vertical acceleration to speed up or slow things down or change their direction in the vertical direction. Okay, cool. Equations. Well, there's really only one equation, so I guess we'll just write the one. So equation is simply the change in velocity that an object experiences divided by the change in time during which that change in velocity occurred. So acceleration, once again, that is the change in velocity that an object experiences divided by the change in time during which that change in velocity occurred. Okay. And that's, again, tracking that with the units velocity meters per second. So if we experience a change in velocity, something could speed up and maybe the change in velocity is 5 meters per second. It's going 5 meters per second faster than it was before for that change. And the time might be 3 seconds. So 5 over 3 would give you the acceleration in that case. So meters per second divided by seconds, that's what gives you the seconds squared. Because if you divide by seconds and then divide by seconds again, now you've got seconds squared in your denominator. And really keep those separate from velocity, right? They are different units. We don't want to say that acceleration is meters per second. We don't want to say that velocity is meters per second squared. Got to keep them separate. All right. Another way to do this, change in anything, and we looked at this with displacement, which is a change in position. Change can be written as final minus initial. So v final, there's our instantaneous velocities again at the exact split second that an object is at the end of a time period. V final minus V initial is your change divided by change in time. That's another way you can write this. Is if instead of the change in velocity, a problem might not give you that. It might not say an object speeds up and the change in velocity is 4 meters per second. They might just give you the values or give you access, a way to find the values. How fast is it going at the beginning or the end? If it starts at 0, it's sitting at rest, it's not moving, and it ends up at 5 meters per second, well, you would do 5 minus 0 to get your change. All right, and that's our equation or way to find or calculate acceleration. And keep in mind with this equation and all the other ones we use, this is not only useful for finding acceleration. If we know what acceleration is, and let's say we know initial velocity as well, and we know the time, we could plug in, okay, acceleration is 5, initial velocity is 1, time is 4. You could plug all those numbers in and then solve for, with algebra, we could isolate and solve for v final if you wanted. So you could use this equation to find more than just acceleration. We could use this equation to find any of the variables that are in it, provided we know what the value or number for the other variables is. Okay, and we'll be doing some of that. A good amount, a decent amount of our problems will be like numerical problem solving, where you plug numbers in and you solve for variables. Okay. Yeah. And again, like you could technically talk about average versus instantaneous, but our acceleration values in our problems will not change. And even if they change, it's not like they're slowly increasing acceleration over time. Our problems might abruptly say or go from one acceleration to another. So for the first 4 seconds, here's your acceleration. It's 5 meters per second squared. Then for the next 4 seconds, you have a different acceleration, and it's 7 meters per second squared. But we're assuming a quick, sudden change in acceleration, which isn't really realistic, but it's going to make our problems more simple, because all of the equations we use for our Big Five kinematics equations will require that acceleration is constant, stays the same amount of acceleration during the time interval that we're dealing with. All right. Lastly, so we've got how far, how fast, speeding up, slowing down, and changing direction. The last kinematics value is time, and this one's pretty straightforward. I think we all probably have a good understanding of it already. Time is simply a scalar value. It is the first one that is primarily scalar. right, acceleration is a vector, velocity is the main one that we use, and that's a vector. Displacement is the main one we use for how far, and that's a vector. Time, however, is a scalar. It is a scalar value answering the question, how long it takes an object to move. And I've already referenced this a decent amount, both in the equations, right? We've already had a couple equations where time or t is popping up, but we've been talking about time periods, time intervals. So in a problem, you'll have like a 5 second time interval you're looking at, and you're like, okay, something is occurring during these 5 seconds. That's right. An observation we're making, or the observer is seeing something happen in this scenario, and the amount of time for which they are observing this object is what we use in our equations and our problems, right? So just how long, either how long does it take an object to move in total, or how long are we observing this object for in this given scenario? Um, what are we dealing with in terms of how long it takes to move? Okay. And keep in mind, it doesn't have to be moving the whole time. We could watch it for 12 seconds, but it's sitting still for the first 4 seconds. That's a possibility. Time time can still pass, even if things are not moving. They could be sitting still for some amount of that time, or the whole time. They might just not move at all. All right. So the base units for time makes a whole lot of sense because we're going to use seconds. If you see minutes, if you see hours, convert them to seconds, because all of our equations require that we deal with the base or default units for that variable. If you try to calculate acceleration and your velocity is meters per second, but your time is in minutes, you're not going to get, first of all, your units would be meters per second per minute, which is weird, but you're not going to get the right answer. Instead you'd want to convert minutes into seconds and do meters per second and then seconds for time. All right, the variable is just t or delta t. Now I will talk a little bit about these. Technically, there is a difference between them, but the difference between them is t, just t by itself, technically refers to a specific point in time, whereas delta t refers to a period of time or a change in time. So let's put that in terms of, I'll draw a little bit of an image here to hopefully illustrate. I'm going to do, it's like a number line, but let's say we start at 0 seconds and we go to 8 seconds. T would be one exact moment in time. 0 seconds is an exact moment in time, t. 8 seconds is also an exact moment in time, t. The change in time is, well, change in anything is final minus initial. So it turns out, for our problems, even when we use t, we still look at that one point in time, like we could say, oh, t equals 8 seconds. Sure, t equals 8 seconds, but the change in time, we're still referencing some other point, because we're not really going to say, oh, let's look at 8 seconds and we won't look at any other point in time, or we don't care about any other point in time. Well, that's not true, because we have to choose some other point in time to say, here's the initial, here's the final, here's the window of time we're looking at. So once we choose 0 to 8 seconds, that change in time is final minus initial, 8 minus 0. Well, that's just still 8 seconds. I should put my units on things, probably. Seconds. Okay. So for the purposes of our problems, there's almost never a difference between like t equals 8 seconds and delta t equals 8 seconds. The only time there would ever be a difference is if you did, like, let's look at t equals 2, or t initial equals 2 seconds. If we did that, we'd say, okay, if we're going from 2 to 8 seconds, The change in time would then be final minus initial 8 minus 2, which would be 6 seconds. So the reality is we don't really use, in this case, let's say we were doing 2 and 8, we don't really use t equals 8 to plug into an equation in that case because we're not concerned with an 8-second time interval. We're concerned with a 6-second time interval. So really, we just use delta t for everything, even though um, you'll see t for a lot of those. So it's kind of confusing to be like, well, they are technically different, but whether you see t or delta t, really what we're doing in every equation involving kinematics and looking at what's happening in some window of time is we're looking at that change in time, right? It's how long is it from the starting point to the ending point? That's our change in time that we're going to be using in the equation. So even when we see t, right, we'd still want to put in the duration of time that we're referring to, not just a single specific point in time. But because we start at 0 a lot of the time, it doesn't matter either way because 0 to 8 is a change of 8 seconds, and the instantaneous split second in time is also 8 seconds. Anyways, that's kind of a side thing. I wouldn't worry too much about it because, yeah, we're pretty much always going to be using a window of time or a duration of time where delta t, even if it says t in the equation, delta t is really what we're using. And if you ever have questions about it, that's totally the sort of thing you could clarify on a quiz or a test, or like confused about time or t and delta t, you can always ask. But okay, sweet, wow. Well, I don't actually know how long this video is, but I do know that I'm probably going to call it here because, well, let me just double check. I wonder if it tells me. It does not tell. Well, I wasn't keeping track, but the two main things that we'd be doing next, or that I would include in future videos, are looking at the big five equations. Now, I want to devote a good amount of time to that because the big five kinematics equations are super important. We're going to use them a lot. I'll talk a little bit about like where we get them from when I do that, and they're like the core of Unit 1 problem solving is using those big five equations in some way. You can use them a lot and use them very effectively in a lot of problems. So I want to devote time to them and going through them and whatnot. So I don't think I'm going to put that in this video. The other thing is graphing. We're going to go through graphs, looking at motion graphs and how to analyze them and what they tell us. And that also takes a pretty significant chunk of time. Okay, well, we're going to call it for this video. Yeah, hopefully between the first two kinematics videos, you now have and again, we're going a bit slow and getting some details nailed down because we really want to understand well what are these physics values we're dealing with. Like when we say time, when we say velocity, speed, acceleration, displacement, distance, we need to know what it is that we're referring to. Is it a vector? Is it a scalar? How do we find it? How do we know what it is? Yeah, so these equations and units, the correct units to use, and an understanding of what all of these variables are is a very important starting point so that we can use them in equations and problems. Okay, well, we'll see you in class and for the next video.